Okay, as I said earlier, for continuous current conduction mode and the discontinuous current conduction mode. So we have two methods of control: pulse width modulation and pulse frequency modulation, which is variable frequency control. So in this case, in pulse width modulation, T on, which is the turn on time, is varied, keeping the chopping frequency or chopping time period constant. Means that this time period over here remains fixed. Only this pulse width turn on time keeps on changing. So here the turn on time is of this pulse width. Here the turn on time has a larger pulse width. So pulse width keeps on changing, but the total time period remains the same. So in this case, turn on time is less, turn off time is larger. So pulse width is smaller. In the second case, the turn on time is larger, but now turn off time has been compressed, made smaller. It means pulse width has been increased, but total time period remains the same. So that's the basic definition of a pulse width modulation. So it means output voltage here is just varied by varying the turn on time only. Means dt. D multiplied by T is varied. So just by varying D multiplied by T, which is turn on time, we can vary the output voltage in buck converter. So if we make turn on time 100% equal to T, turn on time equal to T, turn off time is 0. It's not possible. We have to turn off the switch so that the energy inside the inductor is released and fed back in the circuit. So the continuous current mode of conduction works. So it can never be 100%. So if it can never be 100%, output voltage can never be equal to supply voltage. It must always be below the supply voltage. So it means it is a step down converter. So pulse frequency modulation, which is also called variable frequency control. In this case, chopping frequency is varied, keeping either turn on or turn off time constant. Only the frequency changes, means time period changes, T. Capital T changes, but turn on time or turn off time always remains fixed. In previous case, in pulse width modulation, capital T remains fixed, turn on time keeps on changing, means pulse width keeps on changing. Here, pulse width keeps constant, but the time period keeps on changing. Pulse width is constant. So that's the variable frequency control. So they can be called modulation techniques or control methods. So buck converter can use any of these for the step down output. But the thing is, in variable frequency control or the pulse frequency modulation, the harmonics in the output may become, due to these harmonics at the output, the current can go to discontinuous mode of conduction. So that we have to take care of, so that the harmonics at the output are eliminated. So if they get eliminated, then it's okay. But normally these harmonics can distort the output and can convert the continuous current into a discontinuous current. So depending upon the duty cycle over here. So this is one example. A transistor DC chopper means a transistor is used as a switch in this buck converter. Is supplied with the power from an ideal battery of 100 volts. So the input voltage is 100 volts. DC, because we are talking about DC to DC converter. So the load voltage waveform consists of rectangular pulses of duration of 1 millisecond in an overall cycle of 2.5 milliseconds. Okay, so now we need to calculate the resistive, we have the resistive load, so we need to calculate the duty cycle. And we know that simple definition of duty cycle, turn on time divided by the total time period is a duty cycle. So here the turn on time given is 1 millisecond. And total time period is overall cycle time 2.5 milliseconds. So the duty cycle is 40%, 0.4. And now the average value at the output, which is a DC value at the output, simply we can use the same formula which we derived in previous slides. D multiplied by the supply voltage, it is 40 volts. And now RMS, again, using the same formula we derived, it is root D multiplied by Vs, which is 63 volts. And now ripple factor, again, using that formula, it has 1.2, ripple factor is 1.2. Output power, the voltage at the output, which we calculated 40 volts divided by R. So 40 square divided by R is 160 watts. So 160 watts we have at the output. Okay. Another example. We have a buck, again, because we are talking about buck converter. In this case, we have a converter with low pass filter with these parameters: supply voltage of 50 volts, duty cycle of 40%, inductance value of 400 microhenry, capacitance of 100 microfarad, frequency, switching frequency, that how fast this switch turns on and off. So it is 20 kilohertz, and the resistance at the load is 20 ohms. So the load is 20 ohms. So again, assuming ideal components, means no losses in the power. We need to calculate the output voltage, maximum minimum inductor current. So the output voltage we know, just using the formula we derived, Vs multiplied by the duty cycle is 20 volts. So input is 50 volts, output is 20 volts. So we have stepped down the 50 volts into a 20 volts at the output. Now, maximum current, again, using the formula we derived in previous slides. So use that formula for I max and I minimum. We can see that the maximum value of current is 1.75 amperes and minimum value of current is 0.25 amperes. So the average inductor current is 1 ampere. And delta IL is 1.5, means 1.75 minus 0.25, or I max minus I min is equal to 1.5 amperes. So that is a kind of a, you can say, a change in current every cycle. Because it is continuous current, so every cycle this change in inductor current will happen, 1.5 amperes. Okay, just to mention some of the things, you can see from here the maximum or minimum value of inductor current. They are inversely proportional to the switching frequency F and inductance value L. So if we increase the switching value of F from 20 kilohertz to 100 kilohertz or megahertz, so the minimum value of current will go low. It will decrease. And if we decrease the switching frequency from 20 kilohertz to 10 kilohertz, the minimum value of current will increase. So it means by changing the switching frequency, we can change the continuous current conduction mode into discontinuous, if possible, depending upon the inductance value. And if inductance value is made very large, I minimum is very small. So it can even go to discontinuous mode also, because if I minimum goes very low, it decreases by large value, it can go to 0. So it can convert into a discontinuous mode. So just by changing these parameters, L, F, R can be fixed value because load can be fixed. We can change the load also, but these are the design parameters. L, which is a design parameter, means we can use this inductance value to design buck converter. F, switching frequency of these switches. R is the load given to us, maybe a motor or something, so we cannot change it depending upon the requirement. Okay, so these things, as a designer, as an engineer, you can design any buck converter using these parameters. So using these parameters, you can increase this or decrease this output value based on our requirement at the output. So this is an example. Again, similar. So just using the same formulas we have derived, you can find out the limits of the inductor for minimum value depending upon the requirement. So this can be, so the inductance has to be greater than or equal to the minimum value of inductance calculated, so that the current remains in conduction mode, continuous conduction mode. Okay. Now, going further, we know that in continuous conduction mode, the switching cycle normally is divided into two phases, phase 1 and phase 2, as we have seen earlier. Okay. But this one is, at the input we have 5 volts, or at the output we have a 3 volts. So we want 3 volts at the output. So we want to step down 5 volts at a battery over here into 3 volts at the output. So at the output, maybe we want to run 3 volt DC motor or speaker or any device at the output. But at the input, we have 5 volts. Again, when the switch is on, just I'm showing you now the waveform, because at that time we were doing mathematically. At this, I'm just going to show you that how graphically, and then later on we will see how to go further with designing the controller. So mathematically we have derived. Now graphically how it looks like. So when the switch is on, this switch has 5 volts, because we are assuming all are ideal in components in this circuit are ideal in nature. So at this node we have 5 volts. This one, because this is 0 drop over here, because it is ideal switch, 0 drop. So all the voltage will appear over here at this node, because there is no voltage drop here in this switch. So at this node we have 5 volts. And current starts to increase in inductor. We already know that whenever the switch turns on, the inductor starts to conduct the current, and it starts to store the energy slowly. So same nature we saw in AC to DC converters. And then at the output, we have 3 volts. So that's the assumption we have done. Now when the switch is closed, switch is turned off, so this node will be pulled down to 0 volts, because now this battery is disconnected from this node. Only ground, this node is now connected to the ground through this switch. So ground level is 0 volts. So this node is now 0. So going from 5 volts to 0 volts. Now whatever energy this inductor has stored now starts to release, and the inductor current starts to fall like this. But at the load, the current still keeps on flowing because of the inductor. So whatever energy was stored when the switch was on at 5 volts, now when the switch is off at 0 volts, over here, the energy stored in the inductor is now released through the load same manner. So the output voltage will remain the same. Again, assuming all components are ideal in nature. So it means during turn on of the switch, the output load has some value because of the flow of the current through this direction, like this. The load current flows, and there is a, due to this load current, this voltage drop will happen over here, equal to IL load current into R load, and we have a 3 volts as we assumed. And now when the switch is turned off over here, the energy stored in inductor gets released, and the voltage drop over here, we have same 3 volts at the output. So switching frequency of 100 kilohertz. So we have assumed a switching frequency of 100 kilohertz. So these switches turn on and off at a 100 kilohertz frequency. This switch, again repeating, this switch turns on, we have 5 volts at this node. When this switch turns off, this goes on, we have 0 volts. So these two switches are complementary to each other. If one gets on, this has to go off. If this gets on, this has to go off. Very, very important. Otherwise, there will be a short circuit. And this job is done by the controller to make sure that these switches go on and off alternatively at 100 kilohertz speed. So to make it 100 kilohertz, using the same formulas which we derived earlier, we can calculate the value of inductance and capacitance. Okay, so based on these values calculated, we can find out the value of IL average and the maximum value of IL max, which is this 130 milliampere, IL minimum, which is 70 milliamperes, just using the same formulas we derived earlier. And we have already done 2-3 examples previously. So just using these examples for calculation, we have already calculated these values. Okay, and ripple also we have calculated. Based on the 100 kilohertz frequency, we have calculated the turn on time 6 microsecond and turn off time of 10 microseconds. Okay, so now there are two methods normally used by the controller for buck converter or any converter, DC to DC converter. One is a voltage mode control, another one is the current mode control. There are other methods also, but these are the most popular methods used in power electronics. So we'll start with the voltage mode control. So in this case, again, we'll be talking about the pulse width modulation. This is a control voltage VCT, and this is a sawtooth voltage shown like this. Both are compared just like here. This is the sawtooth voltage, and this is the control voltage in blue. Both are compared with this comparator, and we get the output, which is V high T. That output is shown in red over here. So at these crossover points, when this control voltage is superimposed with this sawtooth waveform, it changes the cross points over here. So let's start from here. From this point, from 0 to dt, this VCT, which is blue color, and when we compare this VCT with this sawtooth waveform, we can see that this VCT is larger compared to this sawtooth, which is V sawtooth, from 0 to dt. So it means we have a pulse width from 0 to dt. And at this crossover point over here at dt, now this sawtooth rises above the control voltage over here. So when sawtooth rises above the control voltage, we have zero voltage at the V high. So the algorithm running inside the comparator, by looking at this waveforms, we can say that if control voltage is high compared to the sawtooth voltage, output must be high. If control voltage is less compared to the, because this comparator is actually comparing these two. So when when control voltage is less compared to the sawtooth voltage, we have a zero at the V high at the output of this comparator. And again over here, the control voltage is now larger compared to the sawtooth voltage. So we have a voltage, high voltage at the output. Again, this control voltage is lower compared to the sawtooth. We have a zero voltage. So this comparator keeps on comparing these two waveforms. And when control voltage is higher, it gives high voltage at the output. And when control voltage goes lower compared to this, it goes to zero. So this is a pulse width we are generating from these two waveforms. Just by comparing these two waveforms, we are generating the pulse width. So that's why we can say it's a pulse width modulation. So we get the pulses. This is the turn on time from 0 to dt. This is the turn off time from dt to t, and so on. It continues to repeat itself. And now this V high, this signal generated from this comparator, is given to these two switches. These switches, S high and S low. So these pulses are now used for switching on and off of these two switches, S high and S low, alternatively. And based on that, we can get this output in rippled form. And now if we have this as a voltage, a control voltage, which is a step input or a step signal, and using this step signal to control this buck converter, we can get this type of a response. Transient in the beginning, and then later on it goes to steady state. So this will be the resulting output voltage. And if we go for a frequency plot or logarithmic plot of this particular system, which has a transfer function between output voltage and a control voltage, which is a step input, we have this classical second order system, which is a response to a step input. And if we plot this response of a step input for the output voltage, we get this frequency plot having minus 40 dB per decade, which is a second order system over here. And now going further, if we want to compensate for that, if we want to design a controller for that so that we can improve this frequency plot, because this frequency plot having minus 40 dB per decade of slope is a kind of unstable in nature. So if we want to have a control on the stability also, so we need to insert a controller in between. What's the job of a controller? It gets the output fed back at the input of the controller and make a difference between input and the output. Input which was applied to this buck converter and output fed back, and we take a difference of this and find out and get the control voltage at the output, which gets generated by the controller. So this control voltage is actually generated by the controller based on the difference between the reference input and the output, actual output, which is fed back. And we get the generated control voltage at the output. Now this control voltage is now fed to the comparator over here, which we saw in the previous graph shown by the blue line over there. Now that control voltage is now superimposed with the or compared with the sawtooth waveform, and based on the comparison between the control voltage and the sawtooth waveform, we get the pulses, and these pulses are now used to switch on and off of all these two devices alternatively. Again, this output is received over here and then fed back. Again, a new difference is calculated by the controller, and based on the new calculation of the difference between output and the input reference, a new control voltage is generated, and that new control voltage is now compared with the fixed sawtooth waveform. A new voltage at the output of the comparator is received, which helps to switch on and off of these two devices differently. It can change depending upon the control voltage. What will change? The pulse width, turn on and turn off time. We can see from here. The turn on and turn off time will change if this control voltage and this sawtooth is fixed. So if this control voltage keeps on changing, this pulse width will keep on changing. So means turn on and turn off time will keep on changing. Again, a new output is received over here and then fed back over here. Again, a new difference between these two voltages is measured to calculate or to generate a new control voltage over here. And this new control voltage is now again compared with the fixed sawtooth. A new voltage, compared voltage, is received over here, which is in terms of pulse width. Means a new turn on and turn off time is received at the output of a comparator, which is again used to switch on and switch off of these devices at a different switching frequency. So the switching time keeps on changing based on the output fed back at the input. Because this input is fixed, sawtooth is fixed, this output keeps on changing. And when this output is equal to this input after some iterations, so now this pulse width will remain the same. So means depending upon the fed back output, the difference is measured. If difference is 0 or according to the specified limit or the desired limit, this control voltage keeps on adjusting itself unless this difference goes to a desired value or 0 value. If any fluctuation is received at the output, again that will trigger the difference. A new control voltage is generated and a new switching frequency or switching pulses are generated. So these switching pulses keeps on changing depending upon the variation at the output. So that's the basic idea of a controller, to adjust the switching pulses by measuring the output. So in that case, the controller keeps on working at every time interval to calculate the or to measure the difference between input and output, and based on the difference as specified, it keeps on generating the control voltage, sending it to the comparator, which keeps on generating a new pulse widths over here or pulse switching pulses over here to keep on changing the switching of the switches over here. Okay, so now how to make this controller stable so that it does not go into unstable mode. So we can add a compensator or add a kind of a controller which compensates. Integrator can be one, or proportional can be one. Proportional is kind of a gain. So this combination of these two terms is called proportional integrator, integration controller, or a PI controller, simple. So integration, normally what it does is it provides high gain at the low frequencies. So kind of a low pass filter. Okay, so let's take a frequency response of the previous system, this one, without PI controller. We haven't inserted any PI controller at this moment. And we already have seen that this is a second order system. We have already seen that this buck converter is a second order system having inductance and a capacitance, creating two state variables. And for two state variables, we have a second order system. So using this, we have this frequency plot over here. So open loop gain, we are talking about not feeding anything back. So the output divided by the difference. So in that case, if we plot it from this frequency over here to this frequency over here, this system is stable. And if we keep on increasing the frequency of operation, this system becomes unstable, because on x-axis, we keep on increasing the frequency from left to right. And till certain frequencies, the system is stable. After some frequency, the system becomes unstable. So minus 40 dB per decade, a second order. It becomes unstable. So for that, for high frequencies, we need to insert some controller, a part of the controller, so that the system becomes stable for even higher frequencies also. So this unstable the system at high frequencies needs to be made stable. Okay. What we need to do is we can insert this PI controller. And this integrator can insert a high frequency zero. So if we insert a zero at the high frequencies, we can make this system a stable system, or we can convert this unstable system into a stable system. So how to insert high frequency zero means zero at high frequencies is just by including the integrator in the circuit. So the transfer function of this integrator is the control voltage at the output, and at the input, it gets the difference between input and output. So if we take a transfer function of this circuit, which at the input, which is the difference between input and output, which is shown by here, and at the output, we get a control pulses over here, or a control signal over here. So the transfer function comes out to be this one. And using this transfer function by inserting an integrator, we can see that at higher frequencies, now the slope has been converted into a first order system. Because it was minus 40 dB per decade, now it is minus 20 dB per decade, which is a first order system. And first order system is always stable system. So what we have done is we have, just by including this integrator inside a buck converter, we have converted this minus 40 dB per stable. So by inserting an integrated circuit in a buck converter, we can convert an unstable system at high frequencies, because we have seen this is at high frequencies. At high frequencies, the system can be made stable. So integrator is a key component in this one. So what are the benefits of this control, which we have seen over here by adding a controller and an integrator? So this is a voltage mode control. Just by comparing these voltages, we are actually controlling the output and controlling the switches. So this voltage mode control, what are the benefits? It is simple. We just have to make a comparator, and just based on this comparator, we can generate a control voltage, and based on that control voltage, we can change the switching pulses. So not much is required, very simple. So requires only Vout to be measured, because Vout is getting feedback, which is measured by the controller, and that's all. So what are the disadvantages? For a stable control loop, the controller has to be slow, below the LC resonance frequencies. But at high frequencies, it is not possible. For low frequencies, we have seen that it was stable. For low frequencies, it was stable. So after some certain frequency, it becomes unstable. So that is the disadvantage. So, and normally it is slow in nature. So what is the solution for this? We can add a current mode control. So just by adding current mode control, we can, again, the same thing over here, just by using this circuit over here. So now we measure the current. This current in the buck converter is measured, fed back to the RS flip-flop, where a reset pin is connected to the feedback or measured current from the buck converter. So this buck converter, at the output, we measure the current, and that measured current is connected to the reset pin of the flip-flop. And to the set pin of the flip-flop, we connect any triggering pulses, any clock signal or any triggering pulses. And the output of the RS flip-flop is connected to these switches, which are switched on and off alternatively. So in that case, we need to measure the coil current, which is inductor current. We need to measure the inductor current with the control current. And control current is the measured current from the buck converter. So we need to compare, in this case, we need to compare the measured current from the buck converter and the inductor current. So this is the measured current or the control current, shown by the blue line over here. And this is the inductor current, the continuous current mode we have seen over here, because we assumed that we'll be doing this analysis for continuous current conduction mode. So we need to compare this inductor current with the control current or the measured current. And when this inductor or coil current is equal or greater than the control current, then the switch turns off, like here. Here you can say the inductor current, the inductor starts to energize. The inductor starts to energize, it reaches its maximum value. Now it becomes equal to that control current. And when it becomes equal to the control current, it switches off. Now the switch goes off. So till this inductor current is below that level of control current or measured current, the switch is on, which is S high switch is on. And as soon as it reaches the same value, which is equal to or greater, the same value of this control current, the switch goes off, it turns off, and so on. The cycle repeats itself. Now, what about this RS flip-flop? When this inductor current is below the value of the control current, the RS flip-flop is set. As soon as this inductor current reaches the value of control current, the RS flip-flop resets itself. And when it resets itself, it turns off the switch. It resets and then sends the signal to the switch to reset itself, means to turn off the switch. So this set reset will decide whether to switch on the switch or switch off the switch. So this is basically a current mode control. So the transfer function of this current mode control, so the output inductor current, which is I coil current, and the control current. So the relation between these two is simply a slope, a constant value, a simple constant value. And based on that constant value, we can decide at what time to switch on and what time to switch off. Okay. So in that case, again, when we go for a small signal model of this for current mode control, so for the small signal model of the output over here, now the thing is that these current mode controlled switches normally behave like a current source. So we connect this current source in a circuit. This is the inductance, which is a coil, and a capacitor and a load. So just now we are replacing this circuit, these components from previous circuit into a current source. So now we need to have a transfer function between input and output. So now input is a current source and output is the output voltage. So we take a transfer function now, which transfers the control current, which is at the input, into a output voltage. So that is V out by IC. IC is the input, V out is the output. So the input control current is transferred at the output voltage. So V out by IC. So it comes out to be a single order transfer function. So stability problem is not there. Single order, which is simple pole. At the denominator we have a pole, at the numerator we have a zero. So if you don't know poles and zeros, maybe I will have a separate lecture on that, or maybe you have already studied the control system, but if you have not, then I will make a separate lecture on that. But because in this lecture it may not be possible to discuss in detail about all these poles and zeros or roots of a quadratic equation of a transfer function. So I'll do that in a separate lecture. But for a single order function, transfer function, the system is stable. Now again, adding the same integrator, which will give us the zero at the high frequencies. So the same integrator over here, which gives us the, if we want to add to this buck converter, which is a second order system, and if we add a current mode control, we can easily make it a stable system. So this is just some example that for a power amplifier in smartphones, these are the requirements. A step response, which is a control voltage, we have seen in previous slides. A step response of 1 to 100 microsecond, depending upon the type of application. So in smartphones, it may be about 10 microsecond or so, and for slower applications, it can be 100 microseconds and even more. So the response time depends for what type of application we are talking about. Switching frequency, normally you can say that for smartphones it is in terms of megahertz, and for some other applications like a simple MP3 player, it can be less, very low, in kilohertz. So again, depending upon the application, the switching frequency is decided. So once you decide the application, based on that, you decide the switching frequency, and then you can calculate the response time. And based on that response time, you can calculate the value of inductance and capacitance and all these components. So previously I showed an example for switching frequency of 100 kilohertz, now a switching frequency of 100 megahertz. So the I max and I minimum values are changed, as well as the inductance values. Same circuit, same buck converter, same topology, but the values are changed because we want to have a high switching frequencies. We want to raise that frequency from 100 kilohertz to 10 megahertz. And based on that, we calculate the value of inductance. And based on that, we can find out, using those equations we derived in previous slides, we can calculate the value of I max, maximum coil current or inductor current, and minimum coil current. So I have used coil current and inductor current interchangeably because inductor is made in terms of coil. So that's why we call it coil also. In industry, mostly they call it coil, and in academics, they call it inductance mostly, but they still use it interchangeably. But I'm giving you both the terms. So the coil current also changes just by changing the switching frequency. So the calculations are same, but the values will be different. Now, again, you can compare it with the previous example or previous case of 100 kilohertz. The turn on time was in microsecond. Now the turn on time is in nanoseconds, as well as the turn off time. So we have shifted from microseconds to nanoseconds because we want to have a higher switching speed. And based on that, we have changed the value of the maximum and minimum currents and the average current. So but the circuit still remains the same. Only the values are different. So that is the beauty of DC to DC converter. With the same DC to DC converter topology, you can change these parameters: switching frequency, inductance, capacitance, maximum current, duty cycle. Here the duty cycle is 50 nanoseconds divided by 150 nanoseconds, because T on plus T off is a capital T, which is time period. So T on divided by time period is duty cycle. Again, I am repeating this one. So this is the practical buck converter. In this practical buck converter, this diode is now replaced by a MOS semiconductor, metal oxide semiconductor field effect transistor. NMOS is N type of MOSFET, PMOS is P type of MOSFET. And you have studied these P type MOSFET and N type MOSFETs in your basic electronic course. So we have these two switches. So this is S high switch, this is S low switch. NMOS is a S low switch. And this is the internal resistance of NMOS, which is RNMOS. We are including these parameters also. And this is the internal resistance of the PMOS. This is the internal resistance of the battery or a DC source. This is the internal resistance of the coil, inductance. This is the diode, a freewheeling diode. This is the parallel capacitor. This is the ESR, which is the internal resistance of a capacitor. This is the output voltage. This is the load current. And now here we have a digital controller. We can also have an analog controller, which we saw in our previous case of buck converter, where a controller was shown in a triangular form. It was an analog converter. Now we can also have a digital converter or digital controller. So these now for this case, for practical buck converter, I have chosen a discontinuous current conduction mode because we have already done the continuous current conduction mode. So I was thinking that for practical buck converter, let's go for the discontinuous so that both type of conduction modes we cover. But the same concept applies for the continuous current conduction mode. Only thing is that it does not have phase 3 and phase 4 in continuous current conduction mode, which we have already seen in the first case. Only two phases. One is during charging and one is during discharging. Here we have phi 3 and phase 3. Okay, let's see. Now this is our practical buck converter circuit we have. So for discontinuous current conduction operation, that this buck converter is now operating in discontinuous current conduction mode. So the main application may be a smartphone application, laptop, or any other portable devices. So they can go to a standby mode. And while going into a standby mode, they can save power. So efficiency increases. Okay, let's start with the phase 1, first phase of this discontinuous conduction mode of buck converter. So in this case, the controller, which is the digital controller in this case, it turns off the NMOS switch because this digital controller is sending the signal to this NMOS as well as to PMOS. And it is getting also the feedback from the Vout in dotted form as is shown by dotted lines. Okay, so in first phase, the controller turns off this NMOS and turns on this PMOS simultaneously. At the same time, it turns off NMOS and turns on the PMOS. Now, we already know that in this phase, when this configuration takes place, PMOS on and NMOS off, the coil current starts to increase and the energy starts to develop inside the inductor. And now at the same time, the current shown by red also goes through this capacitor, charges this capacitor. And we already also know that now the voltage drop happens in the coil. And using Kirchhoff's voltage law, difference or sum of voltages in this, again, I'm simplifying this operation over here, not taking all the voltage drops in each and every component. In practice, we actually calculate each and every voltage drops at every component. But the scope of this course, we have to go for the basic principles and all this. But still, I'm giving you a practical buck converter over here, that sum of the voltages in a loop is 0 as per Kirchhoff's voltage law. So V in plus V out plus V coil is equal to 0. So in that case, we can say whatever voltage we have at over here, so it means V in minus V out is equal to V coil, or V in minus V coil means the voltage at the dropped at the coil. So input voltage minus the voltage dropped at the coil will be received at the output voltage V out. So in that case, the voltage drop at the coil will take place, and the difference between the input voltage and the voltage dropped at the coil will give us the output voltage, which is less than the input voltage, which we have already seen in our previous slides or in that previous case. Okay, but now in this phase, the inductor is completely energized due to the flow of current because of the switching on of this PMOS. Now phase 2, this PMOS is now turned off, NMOS is turned on now. Simultaneously again. One gets off, another gets on, and vice versa. So now NMOS gets on, PMOS gets off. Now this supply voltage, which is a DC voltage or a battery, gets disconnected from the rest of the circuit. So now we are remained with this loop only. Now this inductor, as we already know, will now act as a source of energy. So now it reverses its polarity and it starts to flow the current through the load, the same direction of flow of current. So through load, the same direction of flow of load current will take place, as shown by red arrows over here. So after phase 1, because in that phase 1, the inductor current was increasing because of the energizing of an inductor, and it reaches maximum value over here. It means inductor was completely energized. So now in phase 2, PMOS turns off, and only we are remained with this part of the circuit where inductor acts as a source of energy, and it delivers the current through this load, and which follows this path through NMOS. And now inductor starts to release its energy and gets de-energized. So inductor keeps on getting de-energized by decreasing the inductor current. So it means it is releasing the energy and starts getting de-energized. Okay, so till this point, we can say the coil current at the same time, when it follows this path, the coil current follows this path as well as the path through the capacitor. So this coil voltage now, because it reverses itself, starts to gets de-energized through this one. And this is shown by phi 2 in this graph over here. So after the finishing of this second phase, the coil current does not reach to the value of 0. So in that case, still some energy is inside the coil, because it takes some time to get de-energized. Now phase 3. In phase 3, as we have already seen in phase 2, some part of the energy is already remained in the coil. And this controller has already decided that after de-energizing this amount of energy from the inductor, the NMOS has to be turned off. So after phase 2, the NMOS turns off. And when the NMOS turns off, the phase 3 starts. And now the path followed by this inductor current, which keeps on decreasing due to de-energizing of the inductor energy, will follow the path through freewheeling diode over here. And now, following this path through freewheeling diode, you can say that the coil current decreases even further, because the inductor starts to lose whatever energy remained in this inductor after phase 2. And now, through this freewheeling diode, this inductor is allowed to completely discharge its energy. So whatever energy was stored in phase 1 is now completely discharged in phase 3 through freewheeling diode. So this controller decides, and once this inductor is fully de-energized, now this phase 4 starts. And now this in phase 4, what happens is that this diode will not allow the current in inductor to go negative, because it is a unidirectional device, so it will allow the current to flow in only one direction. So as soon as it reaches 0 after phase 3, the transfer of energy or the flow of energy through from this inductor stops. So in that case, this after this phase, in phase 4, this state of this controller, it will decide for how much time this circuit should remain in this state after this phase 3. So based on the algorithm built inside the controller will decide for how long the circuit should remain in this state where we have a inductor current 0, means no current flows in the circuit. So the current stops flowing in the circuit. And after that stipulated time, the fixed time, the controller starts the whole sequence again from phase 1 again. And then the cycle repeats. So in tabular form, this is how the phases of operation from phase 1 to phase 4 actually, this phases of operation in terms of PMOS, NMOS, and a diode. In phase 1, PMOS is closed, means it's on, NMOS is off or open, and diode is reverse bias, means it's not conducting. In phase 2, PMOS turns off, NMOS turns on. Diode does not get any involvement in it. In phase 3, the PMOS is still off. Now NMOS also goes off. And now diode, this freewheeling diode takes over. Now in phase 4, PMOS is still off, NMOS is still off, and this diode is now reverse biased. And now again, phase 1 starts, where PMOS is turned on. So by turning off these devices for longer periods, the energy is saved, the power loss is saved, and efficiency increases. So this is a simplified version of a practical buck converter. Complete analysis with each and every calculation on each and every component, internal, external, all components is not, or is beyond the scope of this course. It's for advanced level courses. But still, this practical buck converter in simplified form can give you an insight that how in practice these converters look like, and how these PMOS and NMOS actually operate, and how the controller decides when to switch on from phase 3 to phase 4, depending upon the timing, because this x-axis is based on the timing. So controller can decide this phase 1 for how long it will operate in terms of time in microsecond or nanoseconds. And in phase 2 also decided by controller based on the application, that for how long this phase 2 will work, for how many microseconds or nanoseconds, and so on. So this is a simplified form of practical buck converter. So in next, we will be doing the boost converter. Okay, thank you.